This video is going to be on how to find complex roots. So we're going to start off by doing the sum and difference of cubes. That's a type of factoring. And when we do this factoring, we are going to find a real root. But usually when you do sum and difference of cubes, all of your roots are not necessarily real. And so what we mean when we say, sorry, I can't write and talk at the same time. What I mean when I say that we're going to find complex roots is I mean that we're going to find roots that mathematically you can solve for, but they're imaginary. So they don't actually show up on a graph as an x-intercept. And so this means like we used the quadratic formula and we had a negative underneath the square root. So maybe the whole root is completely imaginary. Maybe it has an imaginary piece and a real piece, and that's what makes it complex. But either way, we're going to get some answers that you can't see on a graph. So first, sum and difference of cubes. The formula for this is a to the third plus or minus b to the third. So that's what the original problem will look like, probably without the parentheses. I'd erase them, but I don't feel like it. Okay, so your first factor is going to be a plus or minus b. And then your second factor is going to be a squared minus or plus a times b plus b squared. So, and what I want you guys to notice and here is that we have some different signs. So you'll notice that we have either add or subtract in the original problem. So where difference of squares can only work if you have a minus, sum and difference of cubes actually works with a plus and a minus. But you'll notice that here, the sign is the same as the original. So plus or minus, it means that if you have a plus here, then you're going to use a plus here. If you used a minus over here, then you'd use a minus over there. So we're going to use the same sign for the first factor. For the second factor, we use the opposite sign. So you can see if we have a plus here, then we would use a minus over here. So same sign, then opposite sign, and then at the end, we do always positive. It's just plus. It can't be a minus, it's always a plus. So when we do sum and difference of cubes for factoring, we're just going to remember SOAP. Same, opposite, always positive. Okay, so for our first example, we are going to find all real and complex roots. And if you guys remember, when they say roots, they typically mean to just write your answer as x equals. And, oh, I forgot to put the actual problem there. Erase that. And here's our equation, y equals 8x to the third minus 27. So first thing, we have to write it so it matches our formula. We want it as something to the third plus or minus something to the third. And I can see that x to the third right there, but the 8 and the 27 are not written correctly. So I have to think of something to the third minus something to the third. So 8, if I think of a number to the third that would have made the 8, that would have been a 2. And then something to the third that would have made x to the third would be an x. Something to the third that would have made the 27 would be 3. Okay, so now we are ready to use our formula. So we have 2x to the third minus 3 to the third, and that's going to be a minus b, because this is a minus problem. So we're going to do 2x minus 3, so our sign matches the original problem. And then we have a multiplied by itself, so 2x times 2x is 4x squared. Then we have the opposite sign, and we have a times b, so that's 2x times 3, which gives us 6x. And then always plus b squared, which is 3 times 3, and that gives us 9. So we are going to find where that equals 0. That's how we find all the roots. So typically that first factor is going to give us a real root. Typically that second factor, that quadratic, is going to give us imaginary roots. That is not true 100% of the time, but it is true often enough that it was hard for me to find an example that would actually give you 3 different roots. So let's go ahead and find the real root first. So we know that our real root is x equals positive 3 divided by 2. And then if we are unable to factor the second parentheses, if we're unable to factor that quadratic, typically using the slide divide method, then we're going to have to use the quadratic formula. And slide divide won't work because you're multiplying to 36 but adding to 6, and that's definitely not going to happen. So for my quadratic formula, I have x equals negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Okay, so I'm going to simplify this. 36 minus 16 times 9. You notice I didn't finish the problem, I just did a little bit of simplifying. Okay, 16 times 9. 9 times 6 is 54. 9 times 1 is 9, plus 5 is 14. Okay, so we have x equals negative 6 plus or minus the square root, and so I've got 36 minus 144 over 8. So I've got 14 minus 6 is 8. Let me go back and fix that. Okay. Borrow from the 4, that leaves a 3 in its place. Goodness gracious. Okay, 14 minus 6 is 8. 3 minus 3 is 0, and that's 1. Okay, so positive 36 and negative 144 leaves me with negative 108. Right? And so I just confirmed for myself that I do have a complex root. Okay, so that means that I am going to go ahead, I'm going to change colors here so you guys can see this. I'm going to make this positive and put an I in the front. And since we are in pre-calculus, I do expect you guys to be able to simplify those roots. So 108, if you simplify it, we know it, never mind. 108 is 36 times 3, and 36 is 6 times 6. And so I know that there's a pair of 6s and a leftover 3. So that means that if I simplify that, I get negative 6 plus or minus 6i square root 3, all divided by 8. And the only way that you can simplify something that's written in this form is if you simplify all, I guess you could call it coefficients. If you simplify this and this and this all at the same time, you have to do all 3 of them. You cannot simplify what's underneath the square root sign. So we can only do the 3 numbers that I circled. And what I notice is that all of those are divisible by 2. So I'm going to go ahead and fix that. So divide it by 2, divide it by 2, divide it by 2. So there are the complex roots. I have 2 of those. One for the plus in front of the square root sign, one for the minus in front of the square root sign, and then up there I had that one real root. So altogether 3 roots, which is what I would expect from a problem that said x to the 3rd. Okay, so, and I want to remind you that just because this math looks messy and kind of like convoluted, like, I have to do that and then I have to do that and they're simplifying, it doesn't mean that it's hard math, it just means that it's messy, and in pre-calc it is fair for them to ask us to do messy math. So. All right, so for the next problem, we're going to find complex roots another way. So this would be for a problem you cannot factor. And so for this method, T-H-E-T-I-C. For synthetic division, this method of finding complex roots, we typically find the real roots by graphing the problem on our calculator, okay? So for example 2, we're going to find all real and complex roots for y equals 2x to the 4th minus 5x to the 3rd minus 29x squared minus 73x minus 30. So this time I'm expecting to possibly find 4 roots because this is an x to the 4th equation. And so here to find our real roots, we're going to graph it. And so I took a picture. That's not what I wanted. Hold on. Go back. Okay. I took a picture of my calculator screen when I graphed it. And you do not have to... you guys, I'm so bad at this. There we go. Move you right here. Okay. You do not have to zoom in to be able to see the entire graph for you to figure out what the roots are. The roots are always going to be nice fractions or whole numbers. So I can see that I have a root like right there, and I can see I like covered it up so you couldn't copy it. I'm sorry, so you couldn't count. So to me that first root looks a little bit concerning. I'm not sure exactly where that first one is, the one on the left. It doesn't look like it's quite at -1. The one on the right, however, looks like it's at 1, 2, 3, 4, 5, 6. So I'm definitely going to think the one on the right is 6. The one on the left I need to double check. So the way that you double check a root is you hit, I'm going to put another picture on here. You hit second trace, and you go to that option on your screen that says find the value, and then we plug in the value. So that's what it looks like first. And then an x value is going to pop up, and the calculator is basically saying, like, what x value do you want to plug in? You want to plug in the root that you think it could possibly be. So I thought it might be -1/2, -1/3, something like that. To be honest, if I give you guys a fraction, I'm not going to go for one that is really hard for you to find. And you'll know that you got the right value if when you plug in that number for the x value, you get a 0 for the y coordinate. Okay, so anytime you're doing these and you think you have what the x coordinate should be, you think that you, like here it's -1/2 and 6, if you think you know what they are, go ahead and just do that second trace value, plug it in, make sure that it equals 0, and then you know that you're finding the actual roots, that you're going to do all the work for something that's going to work out in the long run. For students using this method, they most often have issues when they have found the wrong root, when they thought that it was -1 and it was actually -1/2. So just be careful to watch out for that. Okay, so we're going to go ahead and get the problem started. We know that the roots were -1/2 and 6, so I'm going to go ahead and do synthetic division with 6 first. So if you guys recall, you set up the synthetic division by taking the coefficients from the original graph. So it was 2x to the 4th, so I'm going to write 2, minus 5x to the 3rd, minus 29x squared, minus 73x, minus 30. And that number drops down. And then we know that if we're taking something that's actually a root of the graph, then this number over here is always going to be 0. All right, so drop down the 2. 2 times 6 is 12. -5 plus 12 is 7. 7 times 6 is 42. -29 plus 42 is 13. 13 times 6 is 78. -3 plus 78 is 5. And 6 times 5 is 30. Okay, so there was our first step. Now we're going to go ahead and take the other root, the negative 1/2, and we're going to take the numbers that we just finished with. So 2, 7, 13, 5. And again, we're going to start by dropping down the first number. And we know that this is going to be 0. So drop down the 2. 2 times negative 1/2 is negative 1. 7 minus 1 is 6. 6 times negative 1/2 is negative 3. 13 minus 3 is 10. 10 times negative 1/2 is negative 5. Negative 5 plus 5 is 0. Okay, so now we can go ahead and we're going to do the work to find our complex roots. So my result is I have 2x squared plus 6x plus 10 equals 0. And I know for sure that these are going to give me my complex roots, because if they were real, they would have shown up as x-intercepts on the graph. So I've got the quadratic formula. Negative b plus or minus b squared minus 4 times a times c, all divided by 2 times a. Alright, so we'll go ahead and simplify this. So I've got 36 minus 4 times 2 is 8. 8 times 10 is 80. And that's all being divided by 4. So 10 take away 6 is 4. 7 take away 3 is 4. So what we have is negative 6 plus or minus the square root of negative 44, all divided by 4. So I know that this is my imaginary answer. I know that I can fix that square root. So that's 4 times 11. And that's 2 times 2. So I got a pair of 2's to take out in the front and 11 to leave underneath. So I've got negative 6 plus or minus 2i square root 11, all divided by 4. And just like, I'll use pink, just like last time, I can see that all of these numbers are even, so they're all divisible by 2. So I've got x equals negative 3 plus or minus I square root 11 divided by 2. Those are my two imaginary roots. And then my two real roots were the negative 1/2 and the 6 that we found in the original problem. Okay, there is one more type of complex root that I want to show you guys how to find, and that is sum of squares. So here we're going to find all real and complex roots. For y equals x squared plus 4. Okay, so if I want to find the roots, I want to see where that equation equals 0. So I'm going to go ahead and write that. 0 equals x squared plus 4. And I know I've been kind of inconsistent with writing that in the videos, but if you need to write it every time, you're more than welcome. Or if you want to ignore it, you can. This is not factorable because there's no such thing as factoring for sum of squares. So what we're going to do is we're just going to subtract that 4 over to the other side. And then I'm going to go ahead and square root each side. And I know that when I square root to solve an equation that I get the positive and negative version of the answer. So I have x equals positive and negative. And then here I can see that that's a negative underneath the radical, so that's an I, and the square root of 4 is 2. So my solutions are positive and negative 2i. So just make sure that when you are solving sum of squares that you know you cannot factor it, and you are going to get imaginary roots for that. You could do the exact same process if the problem said x squared plus 6. You would just get square root 6 in your answer. Okay, so you can do that whether the numbers are perfect squares or not.